Welcome back, ladies and gentlemen, to our continuing study of electrostatics. Today we're going to take a closer look at two questions, okay? You learned previously that opposites attract, likes repel. Today we want to explore, well, how much? How much do they attract? How much do they repel? Remember that an attraction and a repulsion is really a push or a pull, which means that we're talking about forces. So we want to be able to measure today how much opposites attract or likes repel. The second question we want to answer is, when we say that something is negatively charged, how much? How are we going to keep track of charge? Let's get started. You already know that on an object that's charged,
For example, this conducting sphere, okay, that we don't just have 9 charges here, right? You see 9 negative signs. That doesn't mean we have 9 extra electrons, right? That's just representative of billions and billions of excess electrons, right? Or in the case of this positively charged rod, billions and billions of missing electrons, okay? In order to count how much charge there is on an object, we're going to do something similar to what we do in other areas of our life. When the numbers get really big, we are going to use a bigger unit. So for example, you're going to go to the donut shop, you go order a bunch of donuts for a big event at school. You're not going to go in and say, I want 60 donuts. You're going to go in and you're going to say, I want 5 dozen, right? Dozen being a bigger unit than the single donut. We're going to do a similar thing here. We're not going to say I have 3 billion excess electrons. We're going to use a bigger unit, okay? Now, this bigger unit is called the Coulomb, okay? The Coulomb. And what we want to know is, how many charges does it take to make a Coulomb, right? It takes 12 donuts to make a dozen. Well, how many charges does it take, right? How many electrons, for example, does it take to make 1 Coulomb? Well, it turns out that the Coulomb is actually a monstrously large unit, okay? In fact, it's so large that I'm going to give you an analogy. The analogy I'm going to give you is the analogy of a dump truck, okay? So here's our nifty little dump truck, and it is carrying sand, okay, carrying sand out of a construction site. How many grains of sand would you estimate are in a dump truck? A whole lot, right? Well, it turns out that there are on the order of a billion electrons, okay, 10 to the 18th grains of sand in the dump truck. And it turns out that's about how many electrons there are in a Coulomb, okay? So this Coulomb is a huge unit. In fact, there are 6.25 times 10 to the 18th charges in a Coulomb, okay? Huge, huge amount, all right? So, in fact, let me give you another example of how big this unit is. It's a huge unit. I mean, we've got to have it be big because electrons come and charges come in such big numbers, okay? But even so, this is a large unit, okay? I want you to think of something that you see in everyday life. I want you to consider a lightning bolt, okay? A lightning bolt. Bam! Right, that is a lot of charge. If you think of the damage that's done to a tree, to humans, if they're hit by a bolt of lightning, right? So, turns out that's only about 5 coulombs, right? Now you get an idea of how big of a unit the Coulomb is, okay? Turns out it's so big that it's often simpler to work in smaller versions of the Coulomb. For example, we have a millicoulomb, right? Just like a millimeter, okay? And just like a millimeter is thousandths of a meter, okay? This is a thousandth of a coulomb, right? Or even a microcoulomb, okay? Let me make that a little clearer. That's the Greek letter mu. A microcoulomb is a millionth of a coulomb. A nanocoulomb is a billionth of a coulomb, and sometimes even we have a picocoulomb, which is a trillionth of a coulomb. So sometimes you'll see us use those in this unit, okay? Now, one other question that comes up here, which is, now we know how many charges go into a coulomb. How many coulombs is 1 charge? Okay, if I'm just looking at 1 electron, right, or 1 proton, okay? It turns out that the proton and electron have the exact same charge on each other. It's just one is negative and the other one's positive. And the way that we're going to find that, okay, is we're just going to take this number and flip it around, right? If that's how many charges there are per coulomb, then if we just take its reciprocal, okay, I'm going to write the shorter version here, 1 coulomb per 18th electrons, right? If I flip this around, okay, this is going to come out to how many coulombs per electron, right? Coulombs per electron.
And that's equal to this magic number that you see in lots of places in physics, okay? 1.6 times 10 to the negative 19th, extremely small, right? A billionth, okay, and a tenth of that, 1.6 times 10 to the negative 19th. Okay, so that's a very important number. It's considered a fundamental unit, okay? It's a very basic number. It's the charge on a single proton or a single electron, right? So we might put the number, we might put plus or minus in front, right, if we're talking about a proton or electron. All right, let's go to the next page and see what we might do with this number, okay, how we might apply this to some problem solving. Here's a simple example. I have a huge number of electrons. I want to know how many coulombs that represents, okay? Well, you can see, first of all, that this number is less than 10 to the 18th, right? So it's less than a coulomb, but it's close to a coulomb, right? So let's see how we'd set this up. It's really just going to be a simple dimensional analysis problem. Okay, so I have this many electrons, okay, E for electrons, and just going to do a dimensional analysis here. Okay, so it turns out that for every electron I have this much charge, right, like that. Okay, so I just end up multiplying those two numbers together, and I get this right here. Okay, I could take this number, I could convert it to millicoulombs or microcoulombs, right? You can see that this is a hundredth of a coulomb, right? So the next smallest unit might be a millicoulomb, right? So I could take this 2.06 times 10 to the negative 2 coulombs, and let's see how many millicoulombs that would be. See, for every coulomb, I have 1 times 10 to the third millicoulombs, right? 1 times 10 to the third, 1,000 millicoulombs. So you just multiply those two numbers together and you get 20.6 millicoulombs, right? Just another way to express the same number, right? These two numbers are exactly the same, just using different units, right? 12 inches, 1 foot, same unit. Okay, there is one more way you could do this problem, okay, and that is to use the first number that I introduced to you on the previous page, okay. Instead of multiplying by 1.6 times 10 to the negative 19, you could divide by its reciprocal, right, which is how many electrons in a coulomb. So if that's how many electrons there are in 1 coulomb, like that, right, when I multiply through here, the electrons cancel, and I'm going to get the same number here, 2.06 times 10 to the negative 2 coulombs, which is still 20.6 millicoulombs. Okay, now we've answered how we're going to keep track of how much charge we have. Right, we're going to use this funky unit called the Coulomb, which is really large. A good picture analogy for the Coulomb is a dump truck of sand. Okay, that's how many electrons are in a Coulomb. Now we want to look at the second question, which I posed at the beginning, which is, if opposites attract and likes repel, how hard are they doing that, right? With what force are they pushing or pulling? Okay, so what we're going to do here is we're going to consider two charges. They're called point charges. Okay, point charges means that the charge is concentrated in a small space, right? We don't really have to worry about these things having size, like they don't really have a radius. We're going to just consider them a point. Notice that we're going to use the letter Q to represent a charge. Okay, we could use, right, we use the letter M to represent mass, but now the charge on a mass we're going to represent as Q. Now sometimes you will also see capital Q, okay? You'll see it both ways. So it turns out that there was a fellow who gave us some insight into what this force might be, right? So we're going to just assume here that these two charges are positive, okay? So we know that they are going to repel, right? Likes repel. So they're going to push off of each other this way, okay? With a force, a certain force, right? And it turns out this French gentleman, Monsieur Coulomb, he gave us some insight into what this force might be, okay? And what he came up with is something that might be a little familiar to you, okay? He came up with an expression for the force that looks like this, okay? We would say in words that the force between two charges is directly proportional to the amount of charge on each object, right, Q1, Q2, and inversely proportional to the square of the distance between them. In fact, let's maybe write that this way, d squared. Okay, so the distance between them would be here, like that. Okay, this is known as Coulomb's law. Okay, And the force of repulsion or attraction between two charges is often referred to as the Coulomb force. Okay? Now you see this other letter here, K. Okay, the letter K. And it's called the Coulomb constant. And it's equal to this number here. Right? It's not a number you have to memorize. Okay? But it's a number that will be given to you. Okay? And it just makes, the constant's just there so that when you multiply everything together, your answer in force, right, F, we know that's in newtons, it's going to come out to newtons. All right, we want to wrap up this vodcast with a comparison between this new force, the Coulomb force, and a force that you already know. Does this formula for the Coulomb force remind you of anything? It should. It should remind you of this one right here. Right, you can see that it's identical in structure, okay, to the universal law of gravitation, okay, which is that two masses, any objects with mass, pull on one another, right, with a mutually attractive force. Now remember here, the universal gravitational constant was really different, right? It was like 100 billionth, right? Whereas this number here, the Coulomb constant, is 9 billion. So there's a huge difference here between the constants. And that tells us something about the relative strength of the forces, okay? Which is that the Coulomb force is, relatively speaking, like way stronger than the gravitational force, like 10 to the 20th times stronger. I mean, just a huge difference, okay? So last thing I want to do here is just a quick comparison between the two forces, okay? And I'm going to show you that on the next screen, some of the ways that we can compare the two. Okay, on the next page here, you see a comparison between the two forces. Okay, the Coulomb force, because we deal with positive and negative charges, right? Likes repel, opposites attract. The Coulomb force can be both attractive and repulsive, whereas the gravitational force can only be attractive, right? Masses always attract one another. They both obey the inverse square law. Okay, they both surround objects. They change the space around the objects. Okay. Now, because, back on the Coulomb force, because there's positive and negative, we can actually shield the Coulomb force, right, by balancing out positives with negatives, whereas the gravitational force cannot be shielded. All right, and then finally, as I discussed earlier, because of the constants, the gravitational force is, relatively speaking, incredibly weak, okay, whereas the Coulomb force is relatively strong.